Okay, so now we have seen a scenario where there are multiple tasks that are executing on a system, but a natural question that might arise is, okay, this is fine if each task is just doing its own thing, perhaps it's performing some computation. But in general, I want to communicate between tasks. It could be something as simple as one task is responsible for reading data from a sensor, and another task is responsible for maybe either logging the data to a network or to a file, or to actually perform some computations and maybe actuate something, maybe turn on air conditioning or something like that, right? You don't want everything to be in the same task. If you did, then the whole purpose of the RTOS is sort of defeated. Instead of that, however, if I do have different tasks that are handling this, then how do I communicate between them, right? And the basic problem is, how do I share data between different tasks? Both the simplest sort of approach could be just maybe use the same variable between two tasks, but we already know that the scope of a variable is restricted to the block within which it was defined, right? What that means is, if I have one function and I have another function, a variable declared in one function cannot be used in cannot be even seen in another function, right? And that's part of the how higher, well, even though C is not a very high level programming language, it's considered high level compared to things like assembly, right? And therefore one of the sort of actual benefits of C is scoping, which means that a variable declared in one place is not seen by a variable in another function. And as we have already seen, tasks at the end of the day are functions in C, right? Now the only the variables that can actually be seen across functions are global variables, right? Which means that yes, you could declare global variables, but then you potentially have serious problems that are coming in particular, which task is allowed to modify a variable. If you are only reading from a global variable, maybe it's not so much of an issue because the value doesn't change. But if more than one task tries to change the value of a global variable at a point in time, you can actually end up with very strange scenarios where things can even go seriously wrong. Okay. Now, having said that, global variables are fairly common in embedded systems programming, much more so than in regular C programs, right? And part of the reason for this is because all of the solutions that we have for getting around this problem of having multiple functions trying to modify a global variable at the same time, all of those introduce overhead, and embedded systems, generally speaking, cannot afford the overhead that such things require. So you tend to see global variables used quite a lot in embedded programs. However, it is still not good practice, right? If it is possible to solve the problem in a slightly different way, that is always preferable. Okay, so what's the alternative? We could sort of explicitly pass messages between different tasks, right? And then comes the question of, okay, how exactly do we pass a message and what are the kinds of issues that come up there? We need to sort of synchronize, we need to make sure that a message sent from one task actually is guaranteed to get to another task. We also need to guarantee the order in which the different messages are sent reach the destination in the correct order, and so on. Yeah. So there are multiple different solutions to this problem. What we are going to do is look at one of them in a little bit more detail, right? And this is basically a concept of something called a queue, which is a first in first out data structure. Now it turns out that queues are actually very simple to implement in a language like C. They essentially require some amount of contiguous memory space and pointers, right? And they can be implemented very efficiently. Now the problem is, you need to be careful about how to manipulate it. You need to have some extra check conditions to make sure the queue is not empty when you try reading from it, and that it's not full when you try putting new data into it, and so on, right? But as long as you provide function calls and say, hey, use only these calls in order to either push data into the queue or get data out of it, right? This can be handled fairly cleanly without too much of computational overhead. And by their very nature, they manage to guarantee that the messages or whatever is pushed into the queue will be pulled out in the same order in which they came in, right? One thing, of course, that comes in over here is the fact that a queue is an array it has a certain capacity, number of elements that it can hold, and if I don't choose that size carefully, I can run into problems such as buffer overflow, which basically says that the queue is full and I'm still trying to write data into it, and it can cause problems. So let's take a look at an example of what code looks like over here, right? In the context of FreeRTOS, you basically have access to directly a data structure called a queue, or a queue handle in this case, right? And what it does is there is a function called xQSend and another similar function called xQReceive, right? And what happens over here is that there is a producer task, which once again is an infinite for loop. All it does is it keeps writing data into the queue. It basically prints what data it wrote, right? And then waits for 1000 milliseconds. The consumer, on the other hand, what it does is it basically waits over here to receive data from the queue. As and when it receives data, it basically consumes it, and then it sleeps for 1.5 seconds in this case, right? Now, if you think carefully about it, there is a problem over here. What is happening is the producer is writing data every 1 second. The consumer is only reading one data every 1.5 seconds, which means that I should very rapidly end up in a scenario where the queue fills up. Okay, so let's take an example, take a look at how that actually looks in practice when we try running code like this. So the code that we have over here, once again uses the Arduino FreeRTOS library. It includes the queue.h header file, and as you can see over here, right, basically this is exactly the example that I had. What we do is, in the setup, we also need to create the queue, right? And in fact, over here you might notice that this queue is actually a global variable, right? It is something that is being shared between the producer task and the consumer task, right? So you might wonder, hey, we just said don't use global variables, now why are we doing this? Now this is a specific kind of global variable which is actually being accessed only through specific functions, send and receive, and internally there are mechanisms that you can implement mechanisms to make sure that the non-determinism that comes about when we try accessing it can be mitigated to a large extent, right? But in general, there are ways by which you could actually probably pass the queue itself as one of the parameters to the tasks, but as I said, that basically adds overhead to what's going to get compiled and run, right? So instead over here we actually declare it as a global variable and we use it inside both the functions. It's used over here in the xQSend and also in the xQReceive. Okay, so what we do is we first create the queue out here and we basically say it can store 5 integers, okay, and then I create a producer task by calling the producer task function and the consumer task and start the scheduler. Okay, what happens when I run this? You can see over here that the produced is basically going once every second. If you look carefully, you will notice that it's been going up once every second. And after a while you will notice that the produced has gone up, it's gone to 10, 11 and so on, but consumed is lagging behind, right? But let it run for a little bit longer and you should see that after a while this pattern sort of falls into place, right? The difference between what has been produced and what was last consumed is always 5. In this case, once again, produced of 21 comes out only after consumed of 16. Why is that? Because the queue only had a size of 5. Right? And the point is, what is actually happening over here is that even though we gave a task delay of 1.5 seconds and 1 second over here, effectively the producer is being forced to wait. Even though I want to produce one data every 1 second, the very fact that the consumer is going to only consume once every 1.5 seconds means that I have to slow down, right? I necessarily, if you look at the actual time intervals at which this produced messages are coming, you will see that it's actually coming out only once every 1.5 seconds. Basically the exact same rate as what the consumer task is running, because only when a new place has been created on the queue am I able to put in new data, right? We can easily see this by sort of increasing this or changing this number. Let's make it 10 for example, right? And just to sort of see the result more quickly, I am going to reduce these numbers from 1000 to 100, right. Let us see what happens if we run this. As you can see, of course, it is running 10 times faster. So, I am just going to stop it, but let us look at the pattern out here, right. Only after I have consumed 35 can I now produce 35. After I have consumed 34, can I produce 34? In other words, since I changed the size of the queue to 10, the difference between produced and consumed has gone up to 10, okay. But what happens if we flip this around? Let us say that the consume goes at 15 milliseconds. In other words, the consumer works fast, right. That is all I am changing, right. So, now in this scenario, when I run it, I should see something quite different. And what we would anticipate is that now the producer is actually slow, whereas the consumer is able to sort of access the data fast enough, right. What happens is that every time I produce a number, I immediately consume it. So, the fact that the queue had a size of 10 is now not relevant. I never fill up the queue, right. So, why would I even use a queue in this context? Perhaps I do not need to, or you could have a really small queue. But the point is, queues are also very good at sort of handling any uncertainty that can come into this. Let us say that the producer has some uncertainty rather than just producing data every 100 milliseconds. If it produces data between 100 to 400 milliseconds, or the consumer, rather than finishing every 15 milliseconds, maybe it takes time between 15 to 500 milliseconds to complete, right. In that case, I could actually end up with a scenario where having a queue might result in, I need to have multiple things stored in the queue temporarily, but most of the time the queue is essentially empty, because as soon as I write something into it, the consumer reads it out and makes use of it. So, what has happened in this context is that I am able to use the queue to transfer data from one task, the producer, to another task, the consumer, in a very clean manner, right. I guarantee that there is no sort of loss of information. If there is something else, and if the consumer is not ready to accept the data, the producer will actually have to wait, right. This is called back pressure sometimes, and that automatically sort of makes sure that things run at the right rate so that the processing can actually be completed. So, this approach basically allows us to generate data using the producer, consume data using the consumer, and what we have over here are so called blocking writes and reads. In other words, the producer is not allowed to write into the queue if there is data already present in the queue. There is also a possibility of having something called a non-blocking write, which basically says the producer tries to write. If the queue was full, the producer is not going to wait, right. It is just going to go ahead and pretend that the writing happened and get the next data. What happens? Data is lost, but at the very least the producer by itself is not going to get stuck. That can sometimes be important, especially if the producer has to sort of give an acknowledgement back to someone else saying, okay, I received the data. It might be that your consumer over here is not fast enough, but you do not want the upstream, the source of the data, to actually face that back pressure. And if that happens, you basically end up with a scenario like buffer overflow, right. And buffer overflow basically says, I tried to write data, the queue filled up, any other data that I tried writing into it got lost because it had overflowed the buffer capacity that was available. So, as we can see, queues are a very simple yet effective way of communicating data between tasks, right. They are not the only way by which I can communicate data between tasks. In particular, there are ways by which I might also want to have some messages that need to be sent to multiple different tasks, or I might have one consumer that needs to read from many different possible sources, right. There are multiple different ways that are built up for handling that. Many of them are built on top of basic queuing structures, right. There are in fact custom applications like MQTT, the message queue transport, which can be used in order to actually allow multiple different components of an embedded system to talk to each other. You can even have a scenario where one producer of data publishes information that multiple subscribers can then read from. The way that works is, the moment something is written into the queue in turn triggers an event that is then sent to multiple different subscribers who might be interested in that particular data. Either any one of them could pick it up, or the data could also be sent to all of them, broadcast to all of them, right. So there are many variants on it. The queue is the most simple and a nice clean way of managing communication between tasks. So now that we have seen how we can communicate between tasks, the next question that might come up is, okay, that also means that we might want to know what is the time relation between tasks. In other words, something called synchronization. I want two tasks to work in sync with each other, right? Every time some data is produced in one place, I want to make sure that the second task also wakes up and is able to perform some computation and then update the state of the system, right. And in particular, I might also have a scenario where maybe two tasks are trying to use the same resource, right. It could be a serial port for communication, it could be a network card, it could be a disk file that needs to be shared between two different devices, right. In each of those cases, I have requests coming from multiple tasks, and I need to sort of have some kind of a synchronization that says, okay, wait, all of them need to stop at a certain point. One of them will be given the access, the others need to wait until this one has finished and then take over. So in order to do that, that's another important facility that operating systems need to provide. And intertask synchronization can be thought of as one aspect of communication, right. In general, one of the more common scenarios is for controlling access to shared resources, and it's a form of signaling, right. It basically allows us to send a signal from one task to another. It could be used in order to indicate the task has completed, or it could be that certain data is available in a buffer and therefore do something with it, or it could be that, hey, I'm done with using this resource, maybe somebody else can take over, right. But we need some kind of mechanism that we can use in order to signal this information from one task to another. There are many different approaches used for this, right, and the one that we have seen so far is simply the queue. Task 1 just enqueues information onto a data structure called a queue, and task 2, as and when it sees information in that queue, it basically reads it and processes it, right. Now this works fine if all I want to do is communicate or push data from one place to another, but there are a number of other things that could happen, right, and there are a couple of those in particular that I'll be talking a little bit more about. There is something called a semaphore, which is used in order to essentially control access to shared resources, right. What happens in semaphores is, let's say task 3 and task 4 have, both of them require access to a shared resource. Task 3 needs to explicitly give control of the semaphore to task 4, and then task 4 basically takes it, performs something with it. During that time, even if task 3 becomes ready, it cannot use the resource. So what happens is task 4 eventually, once it is done with its work, will have to give the semaphore back, at which point maybe task 3 or maybe someone else could in turn take over and say, okay, I'll take the semaphore, and as long as I'm holding it, nobody else can, right. A special case of that is something called a mutex, a mutually exclusive control variable, right. And what happens in the context of a mutex is that literally I have only one resource and only one task is allowed to access it at a given point in time. Whoever needs to access it needs to be able to lock the resource so that nobody else can manipulate it at that point in time, right. So a mutex in some contexts can be thought of as a special case of a semaphore, right. But there are a few other differences between them as well. Okay, what we are going to do is just look at a very high level example of some of these. Once again, the exact detailed study of these things can take you fairly deep into the theory of distributed system design, right, or concurrent system design, which is more or less beyond the scope of what we have here. Right now we are only looking at a high level understanding of what these things do. Now what exactly does a semaphore do? It basically counts the number of times a particular resource is acquired, okay, and if more tasks are waiting, they wait for the count to come below the limit. An example of this could be something like, and the way to look at it might be that you have 3 cashiers sitting at in a bank, right, and a queue sort of builds up, right, waiting for the cashiers. Now since there are 3 cashiers over there, as and when one becomes free, one person can go there, but as soon as all 3 are occupied, the next person in queue just has to wait, right. But the moment one of the cashiers completes their task, that person exits from the cashier's counter and the next person can come in there. You can think of that as sort of, there is a semaphore associated with each of these cashiers. As and when one of them becomes free, it gives that semaphore back, or basically reduces the count of how many are active elements over there, so that the next person standing in the queue can take that semaphore and basically say, okay, now I am increasing it back to 3 in this case, which means that all the 3 cashiers are occupied. Okay. Now there is a potential problem that happens when I am sort of incrementing or decrementing this count of the number of active resources, right, which is that in the process of, between the time that I actually check the value of the count and increment the count, in between those it is possible that I got an interrupt which actually did something else and made one of the resources either disappear, or it could be that something else actually took over and occupied that resource, right. So that's essentially what's called a race condition. You are doing 2 things very quickly, at least you think you are doing them very quickly. You check something and then you increment it, but in between the check and the increment something else can happen, an interrupt could happen between those 2 instructions. That's where the notion of so-called atomic operations comes into the picture. An atomic operation basically says the checking a value and incrementing it. In other words, I check whether it is less than 3 and increment it, all happen as a single atomic instruction. Either I can check that it's less than 3 and do the increment, and therefore nobody else can basically go and interfere with it at that time, or I check and find that it is 3 or more and therefore I can't do the increment at all, and then I come away, right. It's guaranteed to be in one of those states, and you can never have a scenario where you check and then you try to increment, but by the time you go there to increment, somebody else has already taken over, right. That race condition is avoided by having an atomic operation. These kind of atomic operations can be used in order to actually, you can guard an entire section of code and say that, the access to a particular resource is completely locked during the time that this particular, I put an atomic operation, I lock a particular section of code or some kind of a data structure and say that no other part of the system has access to this data structure until I release that lock. Okay. Semaphores are a specific case of a type of lock that can be used in such systems. Okay. So let's look at a brief example of what a semaphore type code would look like. So the code that we have over here, right, is basically saying, if you look at this setup, it is creating 4 tasks, right, but if you look at it, you will see that it's basically the same function name, right, the task name, the resource user, there's just one function out here, right, but it's being called with different string tags. So there's user 1, user 2, user 3, user 4, right, and you can also see that it has created a semaphore which basically counts up to 3, right. Now what exactly happens out here? Each of these tasks, what they are going to do is that they are going to basically run an infinite loop, right, where it first tries to take the semaphore, right. If it was able to take the semaphore, it basically says acquired the resource, right. It waits for a certain amount of time. The original code was just waiting for 1 second, but I've sort of changed it so that it waits for a random amount of time, right, up to 1 second. Then prints out saying, okay, this was the task name that or rather it just prints the task name and it says release the resource and gives the semaphore back. The give would essentially decrease the count on the semaphore, take would increase the count on the semaphore, okay. So let's think about what's happening out here. I'm creating 4 tasks that are contending for 3 resources because my semaphore can only go up to 3, So you could think of it as 3 cashiers at a counter, but there are 4 users who are constantly trying to get the attention of the cashier for some reason, right? A more realistic example in the context of a computer system would be something like, let's say you have a large computing system, a database, but there are 3 database connections that are possible, but there are multiple different clients who are trying to connect, or 4 different clients in this case, right? At any point in time, up to 3 of them are allowed to connect. If a 4th one comes, it has to wait for at least one of them to free up. What happens when we run this simulation, right? I'm just going to interrupt this and quickly run over what the code looks like. What you can see is user 1 acquired the resource, user 2 acquired, user 3 acquired, right? And at that point you can actually see that, hey, I don't see user 4 acquired, right? But all 4 of them were basically started at the same time. So at this point in time, what I can see is that 3 of them have acquired it. The 4th one is not allowed to acquire because the semaphore has hit the count of 3. Now after some random delay, user 3 released the resource. This was random because the amount of time that they were delayed over here was random between up to 1 second. The moment user 3 releases the resource, user 4 acquires it, right? Because user 1 and user 2 already had access to it in this case. Now the moment user 2 releases it, user 3 acquires it, because each of these tasks is set up such that as soon as they release it, they go back and wait for, they once again try to do the semaphore take, right? And if you look at what the tasks are actually doing, they are being very busy over here. They are trying to take, and if that did not work, they immediately go back and stand in the queue, right? They are once again waiting over there, so they are sort of spinning around on that. This can be done more efficiently in the way that you don't necessarily use up a lot of CPU clock cycles to do this, right? You can basically wait for something to become free and then process it, but this is one way of handling it. The moment user 3 acquires, okay, or rather the moment user 2 releases it, user 3 once again acquires it. As soon as user 4 releases it, user 2 acquires it. So you can see that whoever was the last one to release is immediately going to be the next one to acquire, right, after the next release. So you have a release, as soon as you release, somebody else acquires it, but as soon as somebody else acquires it, you are the one who's going to acquire, somebody else releases, you are going to acquire, and this pattern sort of continues out here, okay. So semaphores basically allow you to manage multiple tasks trying to access a limited number of resources, as we could see over there, right. Now we also have a special case of a semaphore, in particular something called a binary semaphore, which is a mutex, or a mutually exclusive access control, right. What you could have is that there is, let's say, one data structure that needs to be shared across multiple different threads. Now each of them tries to lock the mutex, right. So the mutex is a variable. It is something like a semaphore, just like you have a semaphore take. All of them, there is also something called mutex acquire lock, right. And if I am able to acquire the lock on this mutex, it means that thread 2 and thread 3 will just have to wait. The moment I acquire the lock, I protect and I can access the resource, right. And at some point in time, I will release the lock, at which point I will go back to whatever I am doing, because I don't need that particular resource anymore. The next one that was trying to access this could potentially get access to the mutex and then go there. Now the important thing is, when you have a mutex like this, it's not as though thread 2 and thread 3 automatically go into a queue and are going to be given the access to the data structure in the order in which they came to request for it. They have to sort of keep waiting over there, and as and when it becomes free, they access it and do something with it, right? There are many practical examples where this can happen when you have a single shared resource in a system, right, or you have log files or database connections with a limited amount of access, right? Now all of these are so-called locking mechanisms. There is also something called lock-free mechanisms, right, where you don't need to block on a mutex or a semaphore. They rely on the availability of something called atomic operations, and this basically means that they need some kind of hardware support for performing those atomic operations, right. Now I'm not going to get into the details of lock-free mechanisms over here, but there are certain kinds of performance guarantees and progress guarantees that can be studied in these contexts. in the context of embedded systems, they are actually preferable for resource constrained systems because you tend to get higher performance than a lock based system, and it is also possible to completely avoid certain conditions like deadlock, right? But they are also a bit more complex to implement, so it's a trade-off, right? Like with any other kind of engineering, this is also a trade-off which says that yes, if you are willing to accept the slightly more complex type of code that results, you may be able to get better performance and avoid the possibility of deadlock happening in a system, right? We will not be getting into details on how these are implemented or how they work in this case.